Thank you, Madam Chair. Distinguished delegates and representatives, my name is Bailey Cunningham. I am a law student at the Florida State University in the United States. As a student of space law, I feel especially privileged to address this 57th session of the Scientific and Technical Subcommittee of the Committee on the Peaceful Uses of Outer Space. Today, I am honored to share this technical presentation on behalf of For All Moonkind and its partner, the Center for Lunar and Asteroid Surface Science, or CLASS. For All Moonkind is an international, non-governmental, not-for-profit organization. It is our mission to protect and preserve human history and heritage in outer space. CLASS seeks to understand the formation and evolution of the surfaces of celestial bodies so that future exploration missions, whether human or robotic, will be properly equipped to handle any challenges they may face. Together, For All Moonkind and CLASS seek to promote sustainable lunar missions, consistent with the recently agreed guidelines for the long-term sustainability of outer space activities. The LTS guidelines define the sustainability of outer space activities as the ability to maintain the conduct of space activities indefinitely into the future in a manner that realizes the objectives of equitable access to the benefits of the exploration and use of outer space for peaceful purposes, in order to meet the needs of present generations while preserving the outer space environment for future generations. This is precisely why we must talk about landing on the moon. Apollo 17 Commander Gene Cernan once remarked that dust is probably one of our greatest inhibitors to a normal operation on the moon. When he says dust, he means the Lunar Regolith, which is the layer of unconsolidated rocks, pebbles, and dirt that exist on the lunar bedrock. Lunar regolith particles are sharp and angular in nature, resulting in a much more abrasive material than their terrestrial counterparts. Not only is lunar regolith abrasive, it is also adhesive, both mechanically and electrostatically. The experience of the Apollo astronauts illustrates the frustrating and potentially dangerous effect of the lunar dust on human and robotic activity. Problems were experienced with dust being kicked up and covering all exposed areas, leading to increased friction and increased wear and tear, which significantly limited the lifetime of surface equipment. In 1967, Apollo 12 landed near Surveyor 3 in order to recover some of its parts. Back on Earth, it was discovered that the Surveyor spacecraft suffered significant damage directly as a result of the Apollo 12 landing, something that took place more than 200 meters away. The exposed surface of Surveyor that was facing the landing site was thoroughly sandblasted and even pockmarked by regolith. Surveyor was lucky. It was not directly hit by the regolith, as it was located in a slight dip on the lunar surface. Analysis shows that if Surveyor had been in the main ejector sheet, damage would have been 1,000 times higher. The transport of lunar dust induced by landings, which we will refer to as lunar ejecta or the plume effect, and the effects of such dust on hardware provide significant constraints on future lunar landings and future lunar operations. Every time a spacecraft lands on the moon, it has the potential to cause severe damage to any objects already on the moon or in orbit around the moon. During the final moments of lunar landings, the rocket exhaust forms a region of pressurized stagnant gas on the soil beneath the engine nozzle. The gas accelerates horizontally away from the center line and becomes supersonic, lifting and ejecting an abrasive fine dust spray at upwards of 1,000 meters per second or faster, along with rocks that accelerate to 10 meters per second or higher. Since the lunar atmosphere is negligible, the particles continue at that velocity until striking the lunar surface, sometimes quite far away. Indeed, it is hypothesized that some particles will travel almost all the way around the moon before impact. Notably, larger particles generally go slower, with sand-sized particles traveling 100 to 1,000 meters per second, gravel approximately 30 meters per second, and fist-sized coppels approximately 10 meters per second. Ultimately, the fact is that no matter where a vehicle lands on the moon, it will produce ejected particles of varying sizes that will impact at great distances. This creates a hazard not only to the lander, but to surrounding hardware on the lunar surface and to vehicles in space in the vicinity of the moon. Rocks and larger particles may directly damage equipment. The dust spray may ruin surface coatings, reflective blankets, and optics. And the infiltration of dust into mechanical joints may cause friction, jamming, and mechanical wear. The risks extend further than the lunar surface. In the upcoming years, there will be an increased level of lunar activity. With increasing capabilities will come larger and more powerful lunar landers. For a frame of reference, the Apollo lunar module's landing mass was 5 tons. Future landers are estimated to be between 20 and 40 tons. Extrapolating to larger landers, simulations show that ejecta velocities increase logarithmically with vehicle mass. So 40-ton landers eject material generally 50% faster than a 5-ton lander. Preliminary estimates indicate that particles can be ejected completely off of the moon. This is a serious concern for future orbital infrastructure. Research shows the effects of impacting dust could accelerate the end-of-life orbital assets or at least require expensive replacement of components on an unacceptably fast schedule. These insights raise questions for the operation of lunar surface and orbital assets, and coordination even among seemingly disparate lunar activities. As lunar activity looks to move beyond short-duration, self-contained science missions, the potential for damage or mission failure caused by high-velocity ejecta, combined with the potential for geopolitical confrontations over these effects, suggests that a solution must be developed. We have already heard from several delegations this session that we should contemplate safety zones, but zones are simply not enough because the perimeter required to assure safety may be extreme. Moreover, safety zones do little to dispel the visual landing hazards created by the plume effect. Additionally, it has been suggested that lunar ejecta could be blocked using berms, fences, or similar barriers. However, particles colliding in flight will scatter over the barrier. Also, larger particles like rocks loft over the barrier and arc down into the other side, and the berms themselves scatter the particles in the lunar vacuum. We propose the concept of shared lunar landing pads, built in situ, utilizing in situ resources. These shared lunar landing pads will be key to early infrastructure development and sustainable exploration and utilization of lunar resources. In one sense, landing pads are a kind of armor for the lunar surface in that they protect the ground from the highly destructive force of the exhaust plume. Practically speaking, this prevents the ground from becoming a spray of high-velocity projectiles that would necessitate armor for surrounding assets. In the absence of this surface armor, all individual surface systems around the touchdown site will need to be protective, and thus more massive, undermining a mass-efficient mission architecture. Investing in landing pads early is critical for cost control, asset safety, and programmatic durability. These landing pads should be the result of international collaboration, established in internationally agreed locations that afford requisite access to locations as indicated by further exploration and analysis of the resources on the moon. We, for all moonkind and class, believe that nations engaged in, or whose nationals are engaged in, activities on the moon have a legal obligation to mitigate the potentially devastating effects of lunar ejecta. Beyond the responsibilities imposed by the Outer Space Treaty and the Liability Convention, the LTS guidelines tell us that we, as the international community, must take steps towards mitigating the risks associated with the conduct of outer space activities so that present benefits can be sustained and future opportunities realized. With this in mind, we encourage the international community to consider the establishment of a group, perhaps modeled on the Interagency Space Debris Coordination Committee, in order to coordinate efforts to mitigate the effects of ejecta from lunar landers. In the meantime, we are eager to work with colleagues from around the world. We look to the moon as a testing ground for deeper exploration, and yet all of our efforts could be fatally threatened by the existence of the lunar dust and the destructive impact lunar landings can have over the entire lunar surface and even lunar orbit. The development and establishment of shared lunar landing pads may be the only way to adequately address this devastating issue. It is also a vital first step in obtaining the level of international agreement and cooperation that will be needed to assure the long-term success and sustainability of all space activity. For All Mankind will be available for questions and discussion throughout the rest of this STSC. Please also feel free to reach out to our team at the emails indicated on the slide. Madam Chair, distinguished delegates, I thank you for your kind attention.